So in this final section of the module, we're going to look at a subject which has become of considerable importance in the last few years within computer science. And this is a topic called spectral methods, and we're going to be looking at their use in computer science over the next 3 or 4 lectures. And since it's a final section of the module, I'm going to give one final pretentious quote. A lot of the terminology that I'll be using is quite ornate. This quote from Ulysses basically indicates that I wouldn't worry about the words being ornate because they are only big words for ordinary things on account of the sound. So let me just review some background. The term spectral method, this refers to a range of techniques which are used to study the structure of matrices. And these methods have been widely used in settings where matrices are a basic modeling technique. For example, in graph theory, in both directed and undirected cases. When we're looking at images, irrespective of the format of those images. In this area called data science, in machine learning, and in a subject called game theory, which some of you will meet in the final year of the course. So what am I going to do in this section? First of all, I'm going to just review some properties of matrices which develop ideas that we saw earlier when we were looking at vectors. I'm going to introduce very important problem called the eigenvalue problem. And this is a key notion when we are studying spectral methods. I'm going to consider some computational issues that arise when we are trying to find what are called eigenvalues and eigenvectors. Most importantly, I'm going to illustrate how we use these ideas in computer science. And I'm going to use 2 examples. One of the examples is in the use of spectral results in Google's page ranking Google search algorithm. The other method I'm going to talk about is in the use of spectral techniques for image compression. So let's have another look at matrices. We briefly introduced some ideas involving matrices in the second section of the module. And we've also seen ideas such as a Hessian when we were looking at partial differentiation and optimization problems, and in ideas such as the Fourier transform in one of the applications of complex numbers. There are 2 important ideas that we didn't look at when we covered that material earlier. One of those ideas is the notion of what's called an inverse matrix. The other one is the notion of what's called the determinant of a matrix. So before going on to talk about those, let's just remember we had this special matrix called the identity matrix, and all of the entries of this are 0 apart from its diagonal elements, in which all of the elements equal 1. And if we take any square matrix, this has the property that when we multiply that matrix by the identity matrix, the result is exactly the same as if we multiplied the identity matrix by the matrix, and that outcome is just the matrix itself. So the identity matrix doesn't affect a square matrix when we multiply that square matrix by it. Now, matrix inverse, this is a very important idea. If we look at a square matrix, then its inverse is a matrix for which we use this notation, and it has the property that when we take our matrix and multiply it by its inverse, the outcome is the same as taking the inverse and multiplying it by the matrix, and that outcome is the identity matrix. Now, not every matrix has an inverse, so we use this terminology singular matrix to describe a matrix which does not have an inverse. We use the term non-singular to describe a matrix which has an inverse. What about this notion of a matrix determinant? If we take any real valued matrix, there is a real value called its determinant, and the properties of the determinant are central to the existence of an inverse matrix. In other words, for determining whether a matrix is singular or whether it's non-singular. The determinant is also crucial to this notion that I call the eigenvalue problem. I'm not going to talk about computational methods for finding the determinant. Those are given in the textbook. Our principal interest in this idea of the determinant is the following result. The determinant is not equal to 0 if and only if the inverse of a matrix exists. In other words, the determinant is non-zero if and only if our matrix is non-singular. So I've referred to the eigenvalue problem. What does the eigenvalue problem involve? We're given some arbitrary matrix, and what we want to do is to find all of the scalar values for which there is an n vector we can associate with that scalar and that matrix, which has the property that when we multiply our matrix by this vector, then the outcome is exactly the same as multiplying that vector by the scalar value. Okay? So we're in the eigenvalue problem, we are interested in these scalar values. Those scalar values, those with the property that we can find a vector with this relationship, these are called the eigenvalues of the matrix. And their associated vectors, these are called the eigenvectors of the matrix with respect to the given scalar. Eigenvectors are the main object which are used in Google's search algorithm, which involves studying the World Wide Web as a directed graph structure. A lot of the properties that are used in Google's PageRank algorithm dates back to a very famous result in this area from the early 20th century. This is a result which is known as the Perron-Frobenius theorem. So let's have another look in a bit more detail at eigenvalues. The case where a vector is a zero vector, this always produces a solution, but the reasons why it always produces a solution are rather trivial. And for that reason, we don't consider the zero vector to be an eigenvector. The case of a scalar having the value 0. The case of an eigenvalue being 0, this is of interest. This is a non-trivial case. So we first note is that if the matrix we are studying is non-singular, then we only have trivial solutions to the eigenvalue problem. The reasons for that, again, those are discussed in the textbook. In general, finding eigenvalues involves finding scalar values which satisfy this identity. When we take our matrix, when we subtract the identity matrix multiplied by some scalar, then we can find some vector for which the outcome of multiplying this matrix by that vector is the 0 vector. Now what that problem reduces to is finding scalar values for which the matrix formed by taking our original matrix and subtracting the identity matrix multiplied by that scalar, that matrix has determinant 0. That matrix is a singular matrix. Now notice that the matrix that we have here is just our original matrix, but we just subtract the scalar value lambda from each of the diagonal entries. The eigenvalue problem, this notion of eigenvalue, this notion of determinant, and this notion which we met several times of roots of a polynomial, these are very closely interlinked. So we can interpret this problem of finding scalar values which make this determinant take the value 0, we can interpret that as a problem involving finding roots of a polynomial. The determinant of any matrix with some parameter, this may be described as a polynomial of degree n in the scalar value. And it follows from that the solutions to this problem, finding values which make the determinant 0, these are exactly the roots of this polynomial. And this polynomial is called the characteristic polynomial of the matrix. And there's a particular notation that is used to describe the characteristic polynomial, this Greek letter chi applied to the matrix itself. All of the details of those constructions, once again, those are given in the textbook. What we have, however, are two very important consequences. We saw earlier that any polynomial of degree n has exactly n roots. And since we can phrase the eigenvalue problem in terms of examining a polynomial of degree n, what that means is that any n by n matrix has exactly n eigenvalues. The other consequence, we saw that there are some polynomials which have roots which are not real numbers, whose roots are complex numbers. And from that we see it is possible for eigenvalues to be complex numbers. In principle, we could extend the domain of the matrices we're looking at from reals to complex numbers. I'm not going to be doing that. We're going to be dealing only with real valued matrices. It is possible to identify classes of real valued matrices whose eigenvalues are guaranteed only to be real. One particular case of those are the class of symmetric matrices. These correspond to matrices arising from undirected graphs. So how do we order eigenvalues? First of all, we have this convention for writing the collection of eigenvalues. We use this notation and we write the eigenvalues between round brackets because these are not a set, and we write them in this order. And that order, this notation, this form is called the spectrum of a matrix. And the convention that's used is the first eigenvalue we regard as the one which is largest size. Now, bearing in mind that some of these may be complex number, the notion of size that's used here is the notion of modulus from complex values, from complex numbers. So the order here, this eigenvalue has larger size than this, has larger size than that, and so on, down to the smallest eigenvalue. The sizes may not be distinct. So if we want to distinguish the case where there is a single unique largest eigenvalue, this is referred to as the dominant eigenvalue of the matrix. The largest eigenvalue, whether it's dominant or not, this is referred to as the spectral radius. For complex eigenvalues, what we can show is if we have a complex eigenvalue of the matrix, then the complex conjugate of that value is also an eigenvalue. And what I'm going to be looking at in the next lecture are computational methods for eigenvalues and for eigenvectors.